Hello students. So we are going to talk about the Brownian motion as your next topic in your phase transition unit of statistical mechanics. So the Brownian motion basically is a motion of particles in fluid, and it represents kind of random motion. So if you think like these are the particles in the fluid, and if you want to trace down the path of a particular particle in the fluid, you will see that it starts and it just keeps on moving, changing the direction. So as a result, it gives you the random motion. It was observed by Robert Brown late in 1820s, and rather observed or studied, because it is very natural phenomena to be observed anywhere. So we are going to study how to model this kind of system, how to model the random motion of the particles in the fluid. And then it's not only fluid, but it can be used, this idea or this kind of phenomena can be also applied to understand the other phenomena in the nature. So Einstein tried to understand it, of course, maybe around 70-80 years after the Brown. He's tried to understand this phenomena as a diffusion process. Okay, so he thinks he modeled the process as a diffusion process of these particles in the fluid. So diffusion is something which you might be familiar with. So diffusion is a process you might have seen when you spray perfume in one corner of the room, it just spreads throughout the room. So that the perfume molecules move in the room by means of diffusion. Okay, so mathematically speaking, we are going to write down the diffusion equation and then find out the solution and try to get an expression for this diffusion process, to which will characterize the diffusion process. So we represent rho as our number density of Brownian particles. This basically tells us that number of particles in a given volume of the space at position r and at time t. Okay, so it is a function of position as well as time t. Then we define current density in the fluid of these particles. So basically it is the number of particles moving with per unit time, or net transport of the particles within a given cross section in unit time. So that again depends on where that your unit cross section is taken, and then at what time. And then we have this d as our diffusion coefficient, n as the total number of particles in the fluid. So let's write down the the well-known Fick's law of diffusion, that the current density is directly proportional to the gradient of the number density. So gradient of number density stands for the concentration difference with respect to the location of the value of rho. Okay, so if you have the perfume molecules spread, if you, let's say, spray out perfumes in the corner of the room, and you will see that the concentration of the perfume molecules in that corner will be highest, and then it will be minimum in another corners. And because of that, they actually start diffuse, they actually start moving towards where the less concentration is. So it's also like when you drop a ink in water, you will see that wherever there is no ink, the ink molecules try to reach to those corners or that part of water. So similarly, so this J will define the number of molecules leaving, reaching or moving towards the empty part, and then that will basically be dependent on what is the concentration gradient. If there is no concentration gradient, then there will be no diffusion. Okay, that's what this equation tells you, and the proportionality constant is your diffusion coefficient. Alright, the negative sign is because it moves towards less concentration. Okay, when the concentration gradient is negative, that in that direction the number of the particles move. Oh, we can also use in addition to Fick's law the equation of continuity. So the equation of continuity tells you that the change in the row with respect to time, this is change in the row with respect to position, this is change in row with respect to time, will actually be equal to the divergence of J, the divergence of the current density. And that's a famous the equation of continuity, and if we combine these two equations, it becomes the time derivative of rho can now be defined in terms of space derivative, but it is a second order space derivative, so that becomes your diffusion equation for transient case. If you substitute that there is no change in with respect to time, then this simply becomes del square rho. It's like a Laplacian equation. Okay, so we continue the Einstein's model of diffusion to understand or to model the diffusion, the Brownian motion. So we have this diffusion equation now, and it has a standard solution which gives you that rho is exponential function of the position r, and it's actually square of r divided by time, and then again this diffusion coefficient comes in there, which can be normalized. So, meaning that it can be normalized is if you integrate this current number density of the particles, Brownian particles, with respect to volume of the fluid, then it should give you the total number of particles, because the rho is defined as the number of particles per unit volume, and if you multiply it by total volume, it should give you the total number of particles, and that's what this means. So now we can use this rho in here and then try to get an expression for a quantity called as mean square of position. So it gives you kind of distribution of this gives you the distribution of the particles. So when we substitute the solution of diffusion equation to rho, okay, so this becomes it's kind of exponential integral, and we know how to solve it. So you might be noticing that how to find out the average value. So you know this equation is there, this will give you this gives you the normalization condition, and this is the density. So it's like your if you remember the finding out the average value, it's when you have the distribution, so you can think this as a distribution and then multiply by that quantity gives you the average value, if you remember from our statistical mechanics initial definitions. So that comes out to be r, because r square is there and we want to find the average value of r square, so it becomes r raised to 4, and then rest of the quantities are simply coming out, so 4 pi and n are coming out. Okay, and this particular integral we will have to use little bit of mathematics, some tricks to get the solution. So we have this equation. Now we want to parameterize this equation in terms of like this. So we want to define something called zeta, which will be equal to r upon square root of 4 dt, and now since we have r raised to 4, so we need a square root of 4 dt raised to 4 also, so that comes out to be square of 4 dt, and that is here, so it is 2, and then from here again another half comes, therefore it is 5 by 2. So we have we want to make sure that we get everywhere the same parameter zeta. So here r upon square root of 4 dt square gives you this, but here we just have r raised to 4, so we just divide and multiply by square root of 4 dt raised to 4. Okay, so that square root of 4 dt raised to 4 comes out here, and then for this dr also we have to do that, so therefore this also comes out to be here, and then we define this as zeta, so this becomes zeta raised to 4 e to the power minus zeta square and d zeta, and then you can do this cancellation. And okay, so this gives you this is a gamma integral, and that gives us gamma function of 5 by 2. Okay, so uh, okay, I'm sorry, actually this is wrong. This part is upon 5 by 2, and so this integral gives you the value like gamma of 5 by 2 upon 2, and then gamma of 5 by 2 comes out to be 3 by 4 square root of pi. Okay, and divided by 2, so that gives you 6 dt, and that's how we will get here the average value of square of position gives you the 6 dt. And if we just solve this for a one-dimensional case, we will get 2 dt. So the things to note here is that the average mean square of position is directly proportional to time. So if you allow time if you allow the system to be there for a long time, you will see that x square will have highest value. Okay, so if you think like at t equal to 0, there will be no spread, so you just drop uh, ink drop. Okay, and then that ink drop will simply be at t equal to 0, there will be no spread, so therefore x square, average value of x square will be 0. But now if you let the system to evolve with time, you will see that x square will increase. That means the ink will try to spread itself in the entire system. Okay, so this gives us the Einstein's model gives us that the x square, average value of x square, will be proportional to time. And this is useful because we are going to do one more model that's called Langevin's model, and it is more flexible and better model than this, and which also comes out to be, which also proves this, which also tells us that the average value of position square, that is a spread, will be proportional to time. So we now stop this video, and I will post one more video on this Langevin's model of Brownian motion. Okay, thank you.